This is part 2 of section 7.4. So what we're going to be doing in this lesson is taking it a little bit further from what we looked at in the previous lesson. Before, we were simplifying trig expressions. Now we're going to use that skill to actually prove trig identities. And one of the ways that we're going to do that is to express everything in terms of sine and cosine, very similar to what we did when we were simplifying those trig expressions. We're also going to look at another strategy, which is to create a difference of squares to prove that trig identity as well. There are other strategies that we'll look at, but those are some major ones that we're going to look at for today. Now I have the notation here, as well as your identities. It's still, same rules still apply. Make sure that you are very comfortable with all of these definitions for sine and cosine, as well as all the trig functions here. But especially this, sine squared plus cosine squared is equal to 1. Make sure you know any variation of this as well, such as cosine squared is equal to 1 minus sine squared, or sine squared is equal to 1 minus cosine squared. So these are something that you're going to see often in trig identities, and you want to be able to spot that right away and use substitution in order to simplify. So let's begin by talking about what it means to verify a trig identity. First off, you're not dealing with equations that you're trying to solve. Okay, you're not solving anything. You don't want to look for theta. You're not trying to evaluate anything. What you're trying to do is to manipulate one side of your equation at a time in order to show that it's actually equivalent to the other side. So what we do is we work on one side of the equation, okay? And we usually pick the more complex side. So for example, here would be a pretty basic trig identity that I would prove by working on the left-hand side first. I want to show algebraically that that left-hand side can transform into the right-hand side, okay? So I only look at the left-hand side and I work on the left-hand side. So one of the things that you want to do is make sure that you're checking your, the side you aren't working on for progress. For example, you know, I continue to try to simplify this, and if I don't get any closer to the secant of alpha, I would end up stopping and retrying something different. So I usually have to switch up the strategy that I'm working with if it's not going anywhere. So make sure you're working in pencil, because you're going to make mistakes, and sometimes you're going to go in circles. You're going to arrive at the same thing that you just stated a couple problems, a couple steps beforehand, and you might get frustrated. One of the things too, as a suggestion, is to work up and down. So work vertically as opposed to horizontally. Make sure you're using substitution and other mathematically sound operations. So you cannot add. You don't want to add 3 to both sides, because what you're using here is something called the addition property of equality, and that's only true, you can only use that property if the statement to begin with is true. Since we don't know that this is true, right, we're asking you to verify it, you can't assume that it's equal. So you can never do something to both sides of the equation. So again, to reiterate, you're going to work on one side of the equation only at a time, okay? You have verified the identity, what your objective is for the day, when you show that both sides of the equal sign actually state the exact same thing, okay? So here's some strategies now. 1, make sure you can manipulate and substitute with your identities. We've learned a few so far. As we increase, as we go through the chapter, we're going to learn more identities, and as we show and prove those identities, then you can start to use additional identities. But for now, we're going to stick with our main Pythagorean identity and look at the alterations of that Pythagorean identity. Now you can use this is really handy, change everything to sine and cosine. A lot of times this will simplify a lot of your expressions, so this is a really nice strategy. And add and subtract fractions. So you want to split fractions by sharing the denominator, manipulate your fractions. Sometimes you want to combine fractions, other times you'll want to split them. Factoring expressions is also pretty important. I don't have many examples where you're going to be doing that necessarily, but in your textbook you should be doing that. And make sure you get the same trig functions on each side of the equal sign. Okay, so you have to have eventually the same exact trig functions on both sides. You're going to simplify as much as possible, and you can also use another strategy of multiplying by the conjugate. Alright, so thanks for listening to that spiel there. I know that's a lot of words all at once, but it's important to understand that you're going to end up, kind of going in circles. There's problems where I start it, and then I end up erasing all the work and starting over again because I didn't get anywhere the first time around. So these can be frustrating, but as long as you continue to work through them, you're going to see a lot of the same strategy pop up from problem to problem, and you'll get better at recognizing what strategy to use. So here are 2 examples here where I would like you to try to change the trig identity to either sine or cosine. So for example, I'm working on the left-hand side, okay, so I'm going to show that I'm working on the left-hand side here, and I'm going to change cosecant to 1 over sine, and tangent to sine over cosine. And I'm just going to leave that blank here on the right hand side. Some teachers make you rewrite secant of alpha. I don't like doing that actually, because I'm actually sort of stating now, if I write this, that these two are equivalent, and I don't know that yet, so I leave it blank. I like to do it this way. You don't have to do it that way though. You can write in secant of alpha. Just make sure you're never changing the right hand side, okay? So I'm going to leave it blank. All right, now my next step here is to show that those are going to cancel and leave me with 1 over cosine of alpha. Now I'm very close, but I'm not finished. Now some students will leave it like this. You can't. You need to make sure that you're showing explicitly that 1 over cosine of alpha is actually equal to the secant of alpha. So now we have shown that these two sides are equivalent to one another. So we have verified this trig identity. Now in the next example, I would work on the right-hand side here. One, because it looks slightly more complex, but also if I look at cotangent of theta, I'm just going to spot this real quick, I would end up with cosine over sine and plus 1, and it's not really going to get me a whole lot of places, even if I try to share the denominator here and add. So I'm going to work on the right-hand side this time. Okay, so I've got cosecant of theta, so I'll write that as 1 over sine theta, times cosine theta will keep the same, plus sine theta, same thing, we're going to keep that the same. Now, I will distribute here so that I have cosine theta over sine theta plus sine theta times 1 over sine theta is simply 1. And now I can simplify here. The cosine over sine theta is the cotangent of theta plus 1. I have now shown explicitly that the right-hand side and the left-hand side are in fact the same. So I've verified this trig identity. Now in problems 3 and 4, I want to use a new strategy, which is multiplying by the conjugate. In objective 2, I actually stated this as creating a difference of squares. That's what happens when you multiply by the conjugate. So I'm going to look at the left-hand side here of this equation. I'm going to work on the left-hand side to show that this trig identity is true. So I take 1 minus sine beta, and I'm going to multiply by its conjugate, 1 plus sine beta. So 1 plus sine beta over 1 plus sine beta. And notice I'm only going to continue to work on the left-hand side here, so I don't want to, manipulate anything on the right yet. Now, in the numerator, I'm going to keep that cosine of beta times 1 plus sine beta. Okay, and in the denominator, I'll have 1 minus sine squared beta. So I just created a difference of squares here by multiplying by the conjugate. And now I recognize the denominator as a variation of sine squared beta plus cosine squared beta equaling 1. If I subtracted that sine squared beta, I'd end up with cosine squared beta is equal to 1 minus sine squared beta. So therefore, I will substitute a value in here as cosine squared beta. So in the numerator, I have cosine of beta times 1 plus sine beta over cosine squared beta. Now, I see that I can cancel one of these cosines. So now I have just cosine beta in the denominator. So I'm actually going to, instead of writing it to the right here and working horizontally, I'm just going to draw an arrow here. Sorry, there's not much room here to show I'm still working on the left-hand side. I have 1 plus sine beta over cosine beta. And this is exactly what I wanted to show. If I look at the right-hand side, I have explicitly stated that these two sides are in fact equivalent to one another. Okay, now problem 4 is sort of a beast of a problem. I actually don't think you're going to have enough room here unless you write really, really tiny or you get another piece of paper. So I do want you to see this type of problem though, because one, not all identities are super short. A lot of them you might have to work through quite a bit. So this is actually using the strategy of completing the square, or I'm sorry, of creating the difference of squares. But it's a slight variation on that. It's a little bit more complex. So when I look at this, I look at the left-hand side, okay, and I want to manipulate the left-hand side, and I want to multiply by the conjugate here. Now, it might not be as easy to recognize what the conjugate of this would be. What you want to do is actually group this together and think of this as like one term, okay? So the conjugate here would be sine theta plus cosine theta plus 1, don't switch that sign and make that subtraction here. So you want to keep these together as one term. Okay, so if I were to write this out, so I'll be multiplying here by the conjugate that's sine theta plus cosine theta plus 1. Okay, now in the numerator, I kind of have a huge foiling thing here to do, but I can make it a little bit easier on myself if I, again, group these two terms together, so that when I FOIL, I treat this as one term times this term, okay? So, all right, we do our first, I always forget outer, right? Outer's next, so this term times this term over here, and then our inner terms, and then our last terms, and so on. So, let's say I do my first terms together. That would be this whole term, sine theta minus cosine theta, times sine theta plus cosine theta. That actually will be convenient because this is a difference of squares. It'll create a difference of squares for us. So we'll keep that in mind in a second. And then let's do our outside terms. So this times 1 is simply sine theta minus cosine theta. For our inner terms, we're going to add now a term of sine theta plus cosine theta. And then our last term will just be 1 times 1, so plus 1. Okay, so there's the numerator. We'll work on simplifying that in just a second. In the denominator, the reason why we're multiplying by a conjugate is to create a difference of squares. So again, let's group the first terms here together. And we create sine theta plus cosine theta squared minus 1. All right, now in the numerator, to simplify this is actually going to be pretty simple since it is a difference of squares. That would be sine squared theta minus cosine squared theta. So here's our first term. I just kind of, sometimes I cross them out as I go through just so I know I've done that already. And then I have a sine theta plus another cosine theta here, which will give me 2 sine theta. Okay, the cosine thetas here will cancel each other. One's negative, one's positive. And then I have that plus 1 out here. All right, so there I'm working through there, and there's the numerator. In the denominator, I still have one more foiling to do. I can use a little bit of a shortcut. Right, if I FOIL x plus 3 squared, I know that's going to be the middle term, or sorry, the first term squared. The middle term will come by multiplying the two, finding the product of our two terms and doubling it, so that would be 6x, and then our last term would be squaring that middle term. So I use that same idea here to multiply this guy in the denominator here, sine theta plus cosine theta squared. So I take our first term, sine theta, and I square that. The middle term is going to come from finding the product, so that would be sine theta cosine theta, and then just doubling that, so that would be 2 sine theta cosine theta. Okay, and then our last term would be this squared, and then I've got that minus 1. Okay, all right, now here comes the work of simplifying a little bit more. Notice that you have in the numerator a sine squared theta minus a cosine squared theta. So that doesn't quite work for us in terms of, you know, sine squared theta plus cosine squared theta equaling 1. I can't just cancel these out. However, I do notice 1 minus cosine squared theta. I can think of that as 1 minus cosine squared theta, which is equal to sine squared theta. So I'm going to substitute in that as sine squared theta plus another sine squared theta. Then I have that plus 2 sine theta out here. Okay, so let's keep working. Sort of running out of room. I'm sure you are too. Hopefully you're still working vertically though. I just think it keeps your work really organized when you can go step by step and look at it, you know, vertically as opposed to horizontally. Okay, now in the denominator, let's see. I have a sine squared theta plus a cosine squared theta. So that would equal 1. Then I'm subtracting 1. So actually these terms all cancel out, leaving me with just 2 sine theta cosine theta in my denominator. Okay. If you're sticking in there so far, man, I hope this isn't boring you to death. I think these are actually really cool because they're all algebra. It's kind of fun. Okay, now in the numerator, I have sine squared theta and sine squared theta, which is 2 sine squared theta. Then I have another 2 sine theta. This is not sine squared theta. So, you know, you have to be so careful about this kind of thing that you don't think of this as like 4 sine squared theta, okay? This does not have a squared. So they're not like terms, so to speak. In the denominator, I have 2 sine theta cosine theta. Okay, we're almost done. In the numerator, I can factor out a 2 sine theta. That would leave me with sine theta plus 1. Okay, and in the denominator, I have 2 sine theta times cosine theta. I'm going to kind of split that mentally for myself, because then I can see that I can cancel these factors, and that would now leave me with sine theta plus 1 over cosine theta, which is exactly what we were trying to prove way back in the beginning. Okay, so now I know that these two are in fact equivalent, so I've proven and verified this trig identity. Okay, next up in 5 and 6, we have a new strategy here. Sometimes it's very easy and convenient to split up your fraction. So that's what I'm going to do here on the left-hand side of number 5. I'm going to let you guys try number 6 on your own and try to keep the lesson a little shorter also, because I do need to get to at least one of these in 7 or 8 as well. So let's work on 5 now. So let's split up our fraction. So because our denominator here is secant A times the cosecant of A, and in my numerator I have a sum, I'm going to split that into the tangent of A over secant of A, cosecant of A, plus the cotangent of A over secant of A times the cosecant of A. Okay, so again, I'm just splitting this fraction up into two different parts. Now I'm going to use that strategy where I rewrite in terms of sine and cosine. So I have the sine of A over the cosine of A over, now this I would rewrite as 1 over the cosine of A and 1 over the sine of A. Okay, so if I were to combine that together, that would simply be 1 over cosine A, sine A. Let's put them closer together here. Okay, then I have plus. On the numerator here, I have the reciprocal, which would be cosine A over sine A, so the reciprocal of tangent. And then in the denominator, secant of A, so 1 over, and let's do the same thing where we keep that in the same denominator here. Both of these are going to be reciprocals, so cosine A, sine A. Okay. Now, let's keep working. Oh, sorry. In the above, I shouldn't have put equals 1, right? We talked about this, but they're not really equivalent yet, so I don't want to write that equals 1 quite yet. All right, now, if I were to divide by this fraction, that's the same as multiplying by its reciprocal. So I have sine of A cosine of A multiplied by the reciprocal here, which would be cosine A sine A over 1, which I'm not going to write in, but actually I'll keep it in there. Okay, now in the right-hand side fraction, I have cosine A over sine A multiplied by the reciprocal here, cosine A sine A over 1. And now I'm just going to start simplifying. I notice that these are going to cancel, right? So I have sine A times sine A, which is sine squared A. Here, again, the sine A's will cancel similarly over to the cosine A's over here on the left side. And I have cosine A times cosine A, which gives me cosine squared A. And this is an identity, right? Pythagorean identity. Cosine squared A plus sine squared A is equal to 1, so this is 1, which is in fact equal to the 1 here, and I verified the trig identity. So I'd like you guys to try number 6, and then we'll move on to 7 and 8. Alright, I'm going to actually let you do number 7 also on your own. I'd work on the left-hand side, so go ahead and try to manipulate this with whatever strategy so far that you want to, because this isn't technically combining our fraction here. I'm going to do this question here, number 8, which is what I was looking for when I write the strategy combining the fraction. So you guys can try number 7. Any of the strategies that we've talked about so far would apply here for number 7. Alright, now in number 8, I want to actually share our denominator. So I want to create one giant fraction here on the left hand side and find a common denominator. So our common denominator would be sine theta times 1 plus cosine theta. So on my left hand side I'd have to multiply by sine theta, so I'd have sine squared theta, and on the right hand side I'd have to multiply by another 1 plus cosine theta. So I actually have 1 plus cosine theta squared all over sine theta times 1 plus cosine theta. Alright, so we're still working on the left-hand side here. Now, in the numerator, I have sine squared theta plus this I will FOIL, so I have 1 plus 2 times the cosine of theta and plus cosine squared theta. Okay, all over sine theta times 1 plus cosine theta. Alright. Now, in the numerator, I have sine squared theta with a cosine squared theta. So this will equal 1. So I have 1 plus this 1 here to give me 2 plus 2 cosine theta all over sine theta times 1 plus cosine theta. Now in the numerator, I realize that I can factor out a 2 here. So let's write all this in here. I could factor out a 2 here and write that as 1 plus cosine theta. And that would be very convenient because then I can cancel out that factor, 1 plus cosine theta. So now I'm left with 2 over the sine of theta, and I am trying to show that this is equivalent to 2 times the cosecant of theta. So now I will write this without that fraction here as 2 times the cosecant of theta, because I have 1 over sine theta, right? So now I have shown that both sides are in fact the same, and I verified our final trig identity. Okay, so I've left you with 2 problems to do on your own. You definitely want to get this practice. It's very important that you just keep practicing and hammering out trig identities, because it takes a lot of practice to be able to recognize, the algebra techniques that you're going to be using. Okay, that's the end of the lesson. I'll see you guys in class tomorrow.